Hi, this is Lab 4, and it is about a spring mass system. The purpose of this lab was to examine and understand the motion of a spring mass system in which the mass swings in an arc while also oscillating on the spring. In this lab, I analyzed a video of a hanging mass attached to a spring using a program called Tracker, and compared the positions to a computer simulation based on the combination of the fundamental principles we have learned so far. We will see that the spring mass system in the video satisfies the energy principle for all the positions collected in the video and the predicted positions from the computer model. Initially, I uploaded the video provided into Tracker. I then set the calibration stick, or the blue line, to 0.7 meters, which is the given length from the fixed point to the end of the spring with the mass attached to it. This fixed point is also our origin, and the mass is hanging in the negative y direction. Then we tracked the position of the mass once it was released from rest. As you can see, the mass oscillated. I then took the x and y position data and copied them into a separate .csv file, which we will later use in our code. Now, I had to incorporate the initial conditions. The mass of the ball was 0.402 kilograms, which was given to us. The initial position of the mass, determined by the data in Tracker, was negative 0.118 for the x value and negative 0.631 for the y value, meters, which was collected from Tracker. The initial velocity was 0 because it was dropped from rest, and the start time was at 0 seconds. Also, the timestamp provided was 1 divided by 210 seconds, and the gravitational constant, g, is 9.78 meters per second squared. Let's take a look at the code. Here the code collects and reads all the data extracted from Tracker and placed in the .csv file I described earlier. Next, I found the spring constant and the relaxed length of the spring using physics. The spring constant, K, was found by using the period of oscillation and the period of the omega formulas, and was found to be 6.83 newtons. Knowing this, I was able to find the relaxed length of the spring at static equilibrium, meaning when Fnet equals 0. But first, let's state that Fnet in the spring's mass system equals the sum of the spring force and weight force, for they are the only forces acting on the system. These codes are located here, and Fnet is then used in Newton's second law. V final equals V initial plus Fnet divided by the mass times delta T. To predict the new velocity of the spring system, and also in the equation RF equals Ri plus the velocity times delta T to predict the new position of the spring system shown here. So then, when Fnet equals 0, the magnitude of the spring force equals the magnitude of the weight force, resulting in the relaxed length of 0.123 meters. Both the spring constant and the relaxed length are put in the code here. Next, I had to code the energy of the system using the energy principle. The energies that are present in the system are the kinetic energy, the gravitational potential energy, and the spring potential energy. Kinetic energy is equal to 1/2 mass times velocity squared. The gravitational potential energy equals mass times gravity times the y position, and the spring potential energy equals 1/2 times the spring stiffness times the stretch, or S. They're coded to this. We must also calculate the change of the energies. The red ball is representative of the data from Tracker, and the blue ball is the predicted position from the computer model. The blue arrow represents the spring force, and the black arrow represents the gravitational force. The graph here on the right shows the position data in the y direction of the red ball and blue balls, and it is clear that the two reflect similar positions. A reason for the discrepancy between the two lines is that the drag force catches up with the spring mass system in the real world, which is not considered in the model. This can cause some slight round-off errors. Overall, the computational model does a good job of predicting the positions of the oscillating mass. I also created a graph that plotted all of the energies of the spring mass system. The blue line is the change in kinetic energy, the red line is the change in the spring potential energy, and the green line is the change in the gravitational energy. All of these add up equaling the yellow line, or the sum of the energies, which is approximately 0. Now let's answer the questions. The spring mass system definitely satisfies the energy principle. The change in energy, or delta E, which is the sum of the change in the kinetic energy, the change in the spring potential energy, and the change in the gravitational potential energy. Because there are no interactions with the system that transfer energy to and from the surroundings, delta E should equal 0. All of the energies of the system were plotted on the graph and cancel out to be 0, which satisfies the energy principle. For the second question, I had to make 2 separate estimates of the oscillation periods, one with data obtained for the x positions in Tracker, and one with the data obtained with the y positions in Tracker. There are two oscillation graphs for two different data. After taking the time it took for 3 complete oscillations and dividing it to find the period of one oscillation, I found that the x position provided a period of 1.619 seconds, while the y position provided a period of 1.49 seconds. In the x direction, the mass swings in a pendulum motion, while the y direction in a spring motion. Even the formulas that calculate the periods are different for each type of motion. The pendulum uses length over gravity, while the spring uses mass over stiffness, causing them to create 2 different periods for 2 different motions. In conclusion, I took a provided video, analyzed it to find out the energies involved within it, and why the object moved as it did. Thank you.